Alright, I'm going to try something new this semester and do video solutions to this test number 1. This test is actually going to serve as future practice tests for this class, so that's why it's titled Practice Test Number 1. Okay, so this basically assumes that you know how to solve first-order DEs for the most part, and that you just need a little bit of help with the step-by-step process with some minimal explanations. So here's our first problem, and you'll notice these first two steps I did here put this into the form of a linear first-order DE. Also notice that if I just rearrange things a little bit, this is a separable DE. You could even move this m over to the right side of the equation if you wanted to. You can do all kinds of things with the algebra, but you can separate and integrate. I'm going to do it the first-order linear way, which involves an integrating factor that looks a little something like that. As always, we walk through the steps in class because it allows us the ability to check our answer kind of halfway through. So we multiply through by the integrating factor. The left-hand side should turn into a derivative of the dependent variable and the integrating factor, which we can check, and it does work in this case because we've done everything right. Integrating then both sides of the equation, we get something that looks like this. And then dividing through by e to the b over mt, we get an answer like that. Now, a lot of people struggle with these problems because there are so many letters floating around. And what I do say on the test is that m, g, and b are all constants, which you would hope because those are the letters that are not the dependent variable, which is obviously v in this case, and the independent variable, which is t. So okay, we solved for v as a function of t down here. We do have an initial condition. The initial condition says that v of 0 is the number v naught. That is also a constant. Plug in t equals 0 and v equals v naught, and we get something like that. And solve for c. Plug c back into our answer for v, and we get a final solution that looks just like this. One thing that I did ask you to notice was that as t goes to infinity, this second term here goes to 0, leaving just a gm over b. And with this model, that is the terminal velocity of a falling object. Okay, the second problem looks like this. This DE needs to be written in some kind of appropriate form. I'm going to get the DE into that form by first dividing through by x and y. Now this is looking just like a Bernoulli DE. There's a y prime term, a y term, and a y to some power term. Putting that DE into this Bernoulli form then, it looks like this. And our first step in class was to divide through by this y to this power here. Alright, writing the D in this form makes it more obvious that our substitution of some variable is y cubed is going to work out for us. That's because if we take a derivative of v with respect to x, the independent variable, we get this term right here, which appears right here. Moving constants around a little bit gives us 1/3 v prime minus 3 over xv equals negative 2. Now this is a first order linear DE, which we have to get into its appropriate form. That means we have to get this v prime term by itself by multiplying through by 3. And we get an integrating factor that's x to the negative 9th power. Now there would be some absolute values on this, but let's see if that integrating factor without the absolute values actually works for this DE. Multiply the DE through by the integrating factor, and the left-hand side should turn into, again, a derivative of the integrating factor and the dependent variable. Again, this is checkable, and it does work, so it looks like everything we've done so far, unless we've made 2 mistakes, is correct. We're going to integrate both sides of that equation pretty easily. We're going to simplify, and we're going to multiply through by x to the 9th power. And there we go. We have our v, which is great, and it's tempting to just box that thing up, but we don't really care about v. We want y. That was the dependent variable way back in our original problem. So what we need to do is back substitute v equals y cubed, and solve for y by raising both sides to the 1/3 power or doing a cube root. Okay, there's no initial condition for that, so we don't need to solve for c. That is going to be the final answer. The next question asks, what is the largest rectangle on which we are guaranteed a unique solution to that initial value problem, which means we're using the uniqueness theorem. So the form for the uniqueness theorem gets y prime by itself. We then have a function of x and y over here on the right side, and I'm just going to call that f of xy. We look for discontinuities in this function. And because x has a square root on it, it's discontinuous where x is less than 0. The theorem then states we have to look at the partial derivative with respect to y of that function, which is this right here, and then we have to look for discontinuities in that function. We've introduced a y to the denominator, so we have a new discontinuity of y equals 0. Then basically the theorem says, okay, draw yourself a little picture. Label your discontinuities. We have y equals 0 here, and we have x less than 0 over here. Throw your initial condition onto the graph. Draw the largest rectangle that you possibly can without touching any of the discontinuities, and we are guaranteed a unique solution to this initial value problem, at least in this region right here. We're going to use appropriate notation here. This is a set of all x and y values, such that it looks like y is less than 0, and x is greater than 0. As far as examples go of what initial conditions might not give us a unique solution, well, anything with a negative x value, or anything with an x value of 0, or anything with a y value of 0. Any of those initial conditions, if we drew it up on this graph, we wouldn't be able to draw a little box around it such that we don't have any discontinuities in that box. So the theorem says we would not be guaranteed a unique solution with this differential equation with any of these initial conditions. Alright, we're moving on to problem. So it's tempting to want to call this a first order linear DE. You could actually solve it that way. But if you just try to bring this term over to the left side of the equation and call it first order linear, you'll notice you have this extra y in the problem, which is not part of the first order linear form. So no matter what you do in this problem, it looks to me like you're going to have to factor a y out first. Now, if you're really determined, you could probably do this using a first order linear method, but it's separable at this point. Now, if you do a problem as if it's separable, you have to make sure you can integrate it. And it looks like if we write the right-hand side in a slightly nicer form, we will be able to integrate that. There it is right there. Just split up the numerator. Integrate the left and the right-hand side, and you get something that looks just like this. Now our goal, if possible, is to get y by itself, and that's going to be pretty nice. We can simplify after a couple of algebra steps here. One algebra trick that we've used so many times in class is we can split up a single exponential with sums and differences up in the exponent into separate pieces that are multiplied together. The other rule that we've used so many times is we can take that negative b and put it up in the power of this absolute value of x. That makes this first term, the absolute value of x to the negative b power. Next term, there isn't much we can actually simplify. E to the c is just some constant, so we can call it a. That looks a little nicer if you rearrange terms a little differently, but I'm just going to keep it like that. Alright, the next problem is a tank problem. And really quickly, we start with 800 gallons of solution inside of a 1,000-gallon tank. That solution has a concentration of 0.1 pounds of, say, salt per gallon. We send a rate into the tank of 3 gallons per minute, which has a concentration of a ½ pound per gallon. And we send a rate out of the tank at 5 gallons per minute. I'm going to define a variable here. X of t is the pounds of salt in the tank for any given time t, and you can kind of see that this is not going to work forever. Whatever model we set up is only going to work in this case until the tank is empty. Sure, we'll still have a rate going in and a rate going out, but the rate going out is going to change and then nothing really happens. So the differential equation is only going to work for certain values of t. Since we have 3 gallons in and 5 gallons out for every minute that passes, this is only going to work for about 400 minutes. Alright, let's set up our differential equation. This is what we call the Ricci-Rocco model. Rate in, concentration in, minus rate out, concentration out. Gives us the change in the pounds of salt in the tank for any given time. Most of this information we're given. But the concentration out changes because it's based on what's actually happening in the tank. Concentration is the pounds of salt in the tank divided by the volume. So how many pounds of salt are in the tank? Well, we set up a variable for that. It changes. What is the volume of the tank? Well, that changes too. It starts at 800, but for every minute that passes, we subtract 2 gallons. So 800 minus 2t. As far as an initial condition goes, x of 0 is the pounds of salt in the tank at time 0, which can be found by just multiplying the concentration times the volume at time 0. That's going to be 800 times 0.1, which is 80 pounds. Alright, now that we've set this thing up, we can go about the business of solving it for the next several steps. This happens to be a first-order linear DE. You'll notice I like fractions. But regardless, we're going to need an integrating factor to solve this DE. The process of integration is a U substitution, which pulls out a factor of a -2 into the denominator. And we end up getting an integrating factor like this. One argument for why we can get rid of the absolute values is that this number in here represents a volume, and we're never going to have a negative volume in this problem. Regardless, we're multiplying through by this integrating factor, and we get something like this when we play with the algebra just a little bit. And at this point, this is checkable. We can tell if we did something wrong up to this point. This does check out pretty nicely. If you're thinking maybe it doesn't, don't forget about your chain rule and your derivative. But we're going to go ahead and integrate both sides of the equation. Integrating, we're going to add 1 to this power. We're going to divide through by that power. Substitution is going to give us another factor of 2 in the denominator. Combine all of these fractions together and you're just going to end up with the factor of 1/2 out in front. To get x by itself, we're going to multiply through by that term to the 5/2 power. Now I just noticed that I had copied a 500 into here for some reason instead of an 800, but this should be an 800 all the way through. It doesn't affect the problem. But right now I'm going to plug in the initial condition, which says that at time equals 0, x is 80, and we get an equation like this to solve. And if I've done this correctly, c should work out to be some crazy number that looks like that. Plug that crazy number into your answer, and we're getting some kind of answer that looks just like this. I think this is a good answer. Now if I was taking a test, of course I would double check everything. But I'm just going to go ahead and move on to the last problem, which gives you this model and tells you to set up a phase portrait for it. And to set up a phase portrait, the main step is to find the equilibria, which means set the derivative equal to 0. M and R are just constants in this problem. So you get one equilibrium at 0 and 1 at R. Let's draw a phase portrait. Alright, I drew in our 2 equilibrium values. Now we need to test some points in between our equilibrium values to see if our slopes are all going to be positive or if they're all going to be negative. A number that's definitely in between 0 and R would be R over 2. A number that's definitely bigger than R is 2R. And a number that's less than 0, I'll just go with p is -1. Alright, for p equals 2r, our slope is going to be m times 2r times 2r minus r. Now you were told that r and m were positive constants, so that is going to be a positive slope. Right here at p equals r over 2, looks like we're going to get a positive number, and a negative number, so that is going to be a negative slope. And finally, if we plug in a population, which doesn't really make sense, but of -1, we will get, let's see, negative times a negative, a positive slope in that region. So I'm going to draw in these slopes. All of our slopes are positive up here, they're negative in here, and they're positive up here. This appears to be an unstable equilibrium, and this one right here appears to be a stable equilibrium. Alright, that is all for now. I hope that helps in some way. If nothing else, hopefully it gives you a nice review, maybe for a final exam or something like that, when you're looking at first order DE. Okay, see you next time.